Hello, my name is DJ Lewis and this is Lab 4 Oscillations. The purpose of this lab was to observe the oscillating motion of a spring mass system that moves in an arc, model the motion of the system using Newton's second law, Vf equals Vi plus F net over mass times time, compare the model's predicted motion versus the observed motion, and graph the energy changes during the motion using the energy principle. Delta E system equals work of the surroundings. I found that this method can accurately model the observed motion of the system and graph energy changes that satisfy the energy principle. Here's my experimental setup with a mass attached to a spring moving in an arc. I use Tracker to extract observed motion data, which can be found in the chart in the lower right corner. This data was exported to a CSV file in order to be compared with the model later. In order to begin my Python code, I had to find some useful values. The spring constant K was found by manipulating the period of oscillation equation. Since this spring was the same as the one seen in the lecture videos, it has the same spring constant value of 6.83. Since the system is initially at static equilibrium, we know that the magnitude of the weight force is equal to the magnitude of the spring force using Newton's second law. L0 was found to be 0.123. Again, the same spring was used in the lecture videos. Now I could create a Python code to model the motion of the system. I placed these initial conditions of mass, position, and velocity into my code. I also initialized the values needed for my interactions, including G, K sub S, L0, L hat, and S. With these conditions, I created a loop that used Newton's second law to predict the velocity and position of the mass after a small delta t. The forces acting on this mass spring system were the weight and spring force. Therefore, the net force could be found by adding the weight and spring force. Recall that F of G equals negative mg y hat and F of the force of the spring equals negative ks times s, where s is L minus L naught. I could then run my code and model the motion of my system. Here you can see the spring force depicted by the blue arrow and the weight force, the black arrow. The weight force stayed constant throughout the model while the spring force oscillated over time. This red ball here is the actual observed motion. Compared to the observed motion, the model accurately matched the motion of the system with little difference, as you can see here. These differences could be caused by other forces unaccounted for. I also had to graph the change in energy of the system over time. In order to do this, I used the energy principle, delta E of the system equals work done by the surroundings. Since I chose my system to be the spring, mass, and earth, there are no interactions from the surroundings doing work on the system. Therefore, delta E equals 0. In this case, the total change in energy is comprised of the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy. Recall that K equals 1/2 mv squared, U sub G equals mg times y, and U sub S equals 1/2 ks times s squared. I plugged these equations into my Python code. With these values, I graphed the system's change in energy. With delta K in blue, delta U sub G in red, delta US in green, and delta E total in yellow, we can make many observations. These changes in energies oscillate with the same period as the position of mass changes. Also, the energy changes are the same size but in opposite phase, i.e., kinetic energy is inversely related to potential energy. The change in kinetic energy oscillates from positive to negative twice as fast as the potential energy changes. And finally, it is important to note that the sum of all energy changes is 0, depicted here by the yellow line. In terms of whether or not the energy principle was satisfied, the answer is yes. If we choose our system to be the mass, spring, and earth, no work is done by the surroundings. Hence, delta E equals 0. As we saw on the energy graph, the sum of all changes in energy was in fact 0. Also, it is possible to have two separate oscillation periods for x and y. By calculating the x and y periods with the first 3 phases, I found that the oscillation in the x direction was slightly longer than the y direction. We can see here that 1.646 seconds is greater than 1.524 seconds. Thank you for your time. Again, my name is DJ Lewis.